It's a pleasure to have Dr Seb Watt come to talk to us. This is his second visit to the Black Country Geological Society. I think he came to do a talk for us around about 6 years ago on volcanic hazards at the time. I previously heard him speak at Birmingham University, so I know that he's a fountain of knowledge on the subject of volcanic hazards. His background is that he has previously been at Oxford University and Southampton and moved to Birmingham as a lecturer in 2013. And as I say, we're delighted to have him come along tonight to speak on volcanic tsunami hazards, with particular reference to Krakatau, Hunga Tonga and beyond. Thank you.
Great, thank you very much, and thanks everyone for coming tonight. So yes, pleasure to be back here. A few years ago I did check the talk I gave, and it was more of a general talk on volcanic hazards. So we're getting a bit more specific tonight, which sort of reflects, I guess, a lot of my recent research interest, which is on volcanic island hazards and volcanic island settings more generally. Which pose a sort of complex set of circumstances, I guess, to managing volcanic hazards for a range of reasons. First of all, because of often isolated island populations, because a lot of small volcanic islands are essentially partially submerged volcanoes. So this sort of offers challenges in terms of usable land and evacuation and the topography of these settings. But also a complexity in terms of the hazard itself, in that there's more scope for the interaction of volcanic processes with water. And when water and volcanic processes mix, that modifies the hazard in a range of ways. You can get the interaction of volcanic masses with water to generate tsunamis, which is mainly what I'll be talking about tonight. But of course, you also have potential to modify volcanic processes directly in terms of the explosive interaction of magma with seawater, as has occurred actually at both Hunga Tonga and Krakatau, which are two of the volcanoes I'll be focusing on tonight. So not much of local interest, obviously, in this talk. We're pretty far from home here, but hopefully still of interest in the general sense of sort of geological processes that are dramatic and can be far-reaching in their consequences. So what we've got a picture of here is the aftermath of the Hunga Tonga eruption in 2022, which was a very large volcanic eruption, probably in terms of the energy release and the intensity of that energy release, the largest since the 1883 eruption of Krakatau, particularly in terms of the atmospheric energy release. So the Hunga Tonga event was measurable globally, in a way, actually, that hadn't really been observed since 1883 and the famous explosion of Krakatau, which again was observable at barographs right around the world, even in Edgbaston, actually. That I could have put some local interest in there, actually. So in the physics building at the University of Birmingham, there is a trace from the Edgbaston Observatory from 1883, which shows the atmospheric pressure wave from the Krakatau explosion circulating the world. And actually, it was detected several times over the subsequent hours to days as it circulated the globe. And these sorts of phenomena are quite unusual and hadn't really been observed again in the same way until 2022 at Hunga Tonga. I think quite likely, actually, because of that seawater interaction with the magma and the intensity of the explosive energy release. So yeah, these are interesting events when we have sort of island eruptions that interact with seawater, and they're interesting from a range of perspectives, but principally I'm going to talk about tsunami generation. Now I'm going to use three examples principally. So the other example that we're going to be talking about, and probably the main focus of the talk, is going to be Krakatau volcano, or Krakatoa, as it's sort of widely known. So this is a volcano in Indonesia, and we can see it here in 2018. After another dramatic event, which you might remember, but is certainly sort of less well known than the 1883 eruption, but demonstrated once again the hazard complexity of this particular volcano. And then the other site I'm going to talk about is probably a volcano that's really very poorly known, which is a volcano in Papua New Guinea called Ritter, which today is a very small island, and you can see it has this sort of distinctive shape as if it's sort of half a volcano, really. So there was a former cone, which was a prominent cone in 1888 until it collapsed. And again, this is a partially submerged volcano, and the entire edifice failed in a very large volcanic landslide, a bit like the Mount St. Helens eruption in many ways. Left behind this remnant sort of half-moon type shape, which was the crater rim from this huge landslide scar, but most of the volcano is about 800 meters beneath sea level. It's still active, it's still growing beneath seawater. So that's all that remains, but this is, I think, quite a sort of visually obvious way in which you can see that a huge amount of seawater would have been displaced by this catastrophic failure of this mountain, this volcanic landform, and this generated a very large tsunami which devastated the surrounding island coastlines. So you can see another island in the distance. Very poorly known, partly because this is such an isolated part of the world, and the impacts of this are not particularly well documented from the time, even though they were certainly severe. Now, so these types of events, these sort of large volcanic tsunamis, are dramatic, can have major local impacts. All three of those volcanoes and events I've just mentioned had very significant regional consequences. But I think they remain an under-recognised volcanic hazard, mainly because they're quite infrequent in the historical record. Not all volcanoes will produce this type of event because you need sort of a particular set of circumstances, principally a fairly small volcanic island or a partially submerged volcano. But I think they warrant attention despite that, because of the severity of the impacts in these events. The examples I've talked about are not the only ones. We could point to the Unzen in Japan, which is again a sort of a classic example really of a complex volcanic hazard. So it's Mount Unzen, which remains Japan's worst volcanic disaster, around 15,000 people, I think, killed in this event in 1792. I may not have got that number right, but it's as I say, it remains the most severe volcanic event in Japan in recorded history. And essentially this was again a volcanic landslide on a near coastal volcano which entered the adjacent bay. People were affected both by the inundation from the volcanic landslide, but then by the tsunami that was generated as this material entered the bay. And actually, when you look at compilations of sort of volcanic hazards, and this is a table listed by fatalities, you'll see that tsunami appears surprisingly high up this list. So actually only second to pyroclastic density currents in terms of sort of direct volcanic hazards. There is this second category that is indirect consequences of volcanic eruptions, which you can see is also very significant. But volcanic tsunamis appears high up this list in terms of the impacts of volcanic hazards. And that's accounted for by a very small number of events that had very severe consequences. So I want to sort of examine, I suppose, in this talk, the factors that, first of all, makes these events complex and difficult to sort of understand and potentially forecast. Key to that, I would argue, is learning from past events. There haven't been that many of these events, but I think we can learn a lot from studying them and revisiting some of these historical events. And that can help us ultimately address this question of how do we better prepare for this type of high impact but low frequency hazard. So the sort of event that doesn't occur very often, but when it does occur, can be very severe in its effect. So first off, I think we need to recognise that volcanic tsunamis are what we call a secondary hazard. So they're a consequence of an eruptive or a destabilising process of a volcanic landslide or of a volcanic eruption that causes some sort of interaction with seawater. So we need that event first, and that's the event that one would seek to forecast, the driving primary event. And if we can understand the timing of that and the type of primary event that leads to a tsunami, then we're maybe better placed to deal with the tsunami consequences. And those types of primary events can be what we'd call pyroclastic density currents or pyroclastic flows, maybe a term you're familiar with. So we've got them here as PDCs. Landslides, so essentially some form of mass movement displacing seawater, or some sort of direct explosive interaction with seawater, perhaps a shallowly submerged explosion, or indeed some combination of these events. And probably in Krakatau 1883, for example, I would argue probably all three of these processes were involved. Possibly in the Hunga Tonga eruption as well, at least two of those processes. So that makes these events complex, particularly if they're sort of involving interaction of multiple volcanic processes. And I'll just sort of highlight this global map, which is a map of large-scale landslide deposits. So like that Ritter Island landslide, Ritter is situated down here, just north of the island of New Guinea. So this is sort of the globally known distribution of large-scale landslides offshore volcanic islands. You're probably familiar, I expect, with the idea of very large landslides on the island of La Palma in the Canary Islands and the extreme tsunami consequences of those. And it's true that offshore the Canary Islands, one can see the evidence of extremely large, so hundreds of cubic kilometre scale landslide deposits. You can see those off Hawaii as well. And to be honest, you can pretty much see them off any volcanic island group where you start to look for these processes, because large-scale landsliding is a natural process on volcanic structures. These are rapidly constructed. They can be unstable for a range of reasons. What I highlight here is this massive gap in the Western Pacific region, which of course is a very volcanically active part of the world, but where there's an apparent sort of absence of these types of events. And that really just reflects, I would say, a lack of knowledge and a lack of observation. So it's simply that offshore many of these islands, there hasn't been submarine mapping, submarine exploration. We simply don't know the history of these types of events in this very volcanically active part of the Pacific, which is where Ritter Island's situated. It's not far from this part of the Indonesian volcanic arc as well, at Krakatau, and it's also the setting for Hunga Tonga, which was essentially a very sort of little studied, unmonitored volcano as well until its eruption in 2022. So there's maybe a bit more potential than we recognise for these types of events, particularly in that part of the world. So we'll now sort of just revisit some of those eruptions. I'll start with the island of Krakatau in Indonesia. Sort of still well known, I think, because of its 1883 eruption. This is a volcano people have heard of because of this infamous event. And I think so well known for a number of reasons, but partly because of that sort of global detection of both the eruption itself, but also the after effects of the eruption. So it really sort of entered the public consciousness at that time. And this was one of the first sort of globally distributed news events, so shortly after the advent of the telegraph, which allowed sort of the news of this dramatic change to spread globally and to be a news story. So this was Krakatau in 1883, actually before that cataclysmic eruption in August 1883. This was probably in May, this drawing in an early stage of that eruption, where we can see an explosive eruption taking place on a volcanic island, and most of this island disappeared ultimately in that event. And then this is Krakatau again in 2018, before another tsunami-generating event. This is the new island of Krakatau, called Anak Krakatau, or Child of Krakatoa in the Javan language. And we can see that it's a fairly steep cone with persistent volcanic activity, much less explosive than in 1883. This is a very different type of magma, a more fluid magma, so less silica-rich than this sort of much more viscous, stickier magma. So not capable of producing explosive activity of this intensity, but what this style of activity has done is very rapidly built up an island in less than 100 years, and that structure was inherently unstable and ultimately reached a point of instability in 2018 and failed. So that generated a tsunami in 2018, which sort of mirrored the 1883 event, but actually with quite a different style of volcanism and quite a different magma composition. So we'll start with 1883. And as I mentioned, that island disappeared in the event. Now, I don't think that's probably the most accurate drawing in the Illustrated London News. But nevertheless, it shows the disappearance of this island as it was a prominent peak before August 1883, and essentially most of the island disappeared in that event, and this caused devastation on the regional coastlines of the Sunda Strait. So Krakatau is situated in the middle of this seaway between Java and Sumatra in Indonesia. And it was the populated shorelines there that were impacted by this eruption and by the tsunami that this eruption generated. That was the main cause of the death toll in this event. Now, as I say, this also sort of led to global effects, globally recognized effects. So this was of great scientific interest at the time. There was a Royal Society commission to go and study the event. It's very well documented as well by Dutch geologists. So there's a huge amount of information about this eruption. And some of that documentation links to effects that were seen, for example, in England with the paintings in London, famous sort of sunsets over Chelsea that were documented afterwards. So these sorts of measures were observed very widely. Now, if we look at the setting of Krakatau, so as I say, it's in the Sunda Straits here between the islands of Java and Sumatra. It's one of a number of volcanoes right through this arc, which relates to subduction down here of the Indian plate between the Eurasian plate. But this particular setting, actually in this sort of bend in the subduction zone, probably with some extension between these two islands, has led to this volcano being partially submerged. And it's formed, therefore, of a group of islands, some of which are older parts of the Krakatau volcanic complex. And the active island was this big prior to 1883, and about 2/3 of that main island disappeared in that eruption. Now, this was an unpopulated island, so it wasn't there weren't people living there, but there were people living on these nearby islands to the north and at coastal towns right round these bays here. And so sort of powerful was this event that it generated a tsunami that had heights of 10 meters, 15 meters in places, extensively around these shorelines, and ran inland in places for several kilometers, so that even at the scale of this map, we can see from this sort of grey area the impact of the tsunami. So that's a 50-kilometer scale, and we can even see at that scale at the inlets and sort of headwaters of these bays where that wave has run in over the low-lying ground. So this really decimated coastal towns. It caused 36,000 deaths in these areas. Okay, there we are. So just to sort of demonstrate the power of this wave, we can see from the photographs afterwards the sort of disruption of metal railroads, of masonry buildings, large coral blocks carried in from the shallow shoreline. So this is a piece of sort of reef-type rock of coral limestone carried inland. You can see a person here for scale standing next to this. So these would weigh tens of tons and were carried in some cases for hundreds of meters inland. And even some sort of famous or well-known stories of the impact. So one of these is this steamship, which was carried 2.5 kilometers inland up this valley and deposited 60 kilometers. This was 60 kilometers north of Krakatau, so you can see how far from the volcano this tsunami still had the power to carry a ship inland and leave it stranded here. And the buoy from this ship is still a monument in this town on Sumatra today. So really dramatic sort of consequences of this. Now, to understand the event itself, actually the driver of the tsunami at Krakatau is still not particularly well known, and this is something that we have been working on and we're going to continue to be working on. One thing we can learn is from the eruption chronology to sort of try to really understand what produced this very large magnitude tsunami. And the first thing to point out is the eruption lasted a long time. First of all, it had been persisting for several months. It started in May 1883, really intensified on the 26th of August over a period of about 12 hours. But that catastrophic tsunami was right at the end of that 12-hour period. The timing of it can be linked to around 10 a.m. on the 27th of August. And there's a surprisingly good record of that pattern of explosive activity from the gasometer pressure gauge in Batavia, which is now Jakarta on Java. So this was detecting air pressure fluctuations, which are recorded here as all these spikes. So it's a record of the explosions taking place in the eruption. And there's a whole series of very powerful explosive pulses, which are probably producing pyroclastic currents that are entering the sea. And there was actually a whole series of small tsunamis detected on the coastline around the Sunda Strait, some of which caused quite a lot of damage, enough even for people to start evacuating and moving inland. But those small tsunamis were dwarfed by the major impacts of the 10 a.m. event, which ran, as I say, for kilometers inland. So something different happened at that 10 a.m. stage of the eruption. So we know that that 10 a.m. stage was not the sort of the normal, if you like, part of that 12-hour explosive cycle. It marked a shift in activity, the culminating stage. And I think, therefore, can't simply be explained by sort of another pyroclastic current alone, but something with a distinct nature that took place at the very end of that eruption. Now, the impacts of that event, first of all, just sort of comment from this drawing taken by probably the geologist who led the most detailed study after the event, Verbeek. And what you can see here is the huge volumes of pumice that were expelled by the volcano. They're floating on the sea here. We can see how this island to the north has been completely stripped of vegetation by both pyroclastic currents and the tsunami. We can see here on this island the impacts of those pyroclastic currents with burnt vegetation and the tsunami that's trimmed the landscape and sort of scoured down to the bedrock here. So we can get these sort of insights and even measurements of the tsunami impact on these islands to the north. So we, obviously from that we recognize the sort of scale of the eruption. We can get some measures of the size of the tsunami. Now the island itself, as I say, was reshaped by this event. So the very final map that's available is from August the 7th. This eruption was ongoing, so it was generating attention, and it was being mapped at the time. This was the main island, Rakata, and the vents were actually in an alignment, a linear structure broadly north-northwest, striking north-northwest. And we can see that the map after August 1883 shows that most of this island has disappeared beneath sea level. So the tsunami generating event caused the disappearance of much of this land and the reshaping of this island here. Coincident with that was a lot of deposition. So this island grew, and this one to some extent, with the deposits of those pumice-rich deposits that were expelled by the eruption. So we're moving a lot of mass from beneath the volcano, from the island itself, and it's being deposited on the seabed in radial directions. So that's, unsurprisingly, that has potential for tsunami generation, either through deposition, but also perhaps through this subsidence process that has reshaped the island. So that's forming what we'd call a caldera, which has a sort of crater-like form, but really it's a subsidence structure that's linked to the failure of the roof of the magma storage system. So if we're expelling several cubic kilometers of material from here, then the roof rock will fail and founder into the crust above this, and that mass is then deposited around the volcanic site. So there's this large subsidence caldera and deposition of the pumice-rich ignimbrite, as we'd refer to it. Now, the counterpart to that gasometer pressure record is the tsunami record, which again is also available from Jakarta. And this shows a series of small tsunamis through that 12-hour phase of the eruption. So as I say, lots of small waves, and then they are really sort of overwhelmed by this enormous tsunami generated by the 10 a.m. event. So you can see the scale of that is utterly different to those small events which were probably generated by pyroclastic currents during the 12-hour eruption. So I think it's quite hard to explain the size of that event simply with a pyroclastic current generated event, but perhaps if that acts in combination with other tsunami generating processes, then we can think of a sort of a more unique source for that 10 a.m. tsunami, which plausibly could have involved an explosion that interacted with seawater. We can see that the volcano at that point must have transitioned from an island to something that was a former island, if you like, and very plausibly could involve magma-seawater interaction. And then we have observations, of course, of that 10 a.m. explosion that was detected very, very widely indeed around the world. And perhaps in combination of that, when you sort of think about the actual mechanics of that island failing, it's quite plausible that there may have been some landslide type processes during the destruction of what was a very steep-sided volcano to something that ultimately was all beneath sea level. And that plausibly sort of gives you processes that at least you can argue make the 10 a.m. event very distinctive. Now, one observation as well, which, this is an image of the Krakatau 1883 deposits on one of those islands in the sort of archipelago of Krakatau. This is me here for scale, so you can see the size of that cliff. And this is all deposited in the 1883 eruption. But what we can see is that this is structurally really quite complex. So it's showing evidence of many pulses of pyroclastic current deposition. So not just one massive event that we might associate with that tsunami, but actually a series of events that probably went on for several hours, which fits with those observational records of the eruption. But later in that sequence, we see a very distinctive shift. We suddenly see a layer that is dominated by these massive, dark, boulder-like deposits of a different rock. So we've got here very pure volcanic pumice-rich deposits, and we've got a switch here to something that's got all sorts of other material mixed into it, these types of deposits are often observed in extremely large volcanic eruptions, actually, and are linked to caldera formation. So at the point where you get the foundering of that volcanic landform and the failure of that structure, you're introducing all sorts of other rock types as essentially that volcanic material is breaking apart, it's moving along faults around the rim of the caldera, and you get the destruction of the volcano. So it seems that we've got evidence here that the event finished with that caldera subsidence, and that would fit with the 10 a.m. timing of that tsunami, and would imply that as well as the pyroclastic currents at this time, you've got the foundering of the caldera and the breakup of that volcano in what's likely a complex set of processes that collectively contributed to that extremely large tsunami. Now, as I say, that wasn't the end of Krakatau. This was the remnant. This is the remnant here of Rakata. You can see the steep wall. This is about an 800-meter high cliff, which plunges down into the sea, and this is part of the caldera that was formed in 1883. But if you recall that map with the north-northwest striking vents, that continued to be the site of active volcanism, but beneath seawater. And in 1927, that island was first observed emerging above sea level, essentially at the same point where that 1883 eruption had been happening, but erupting a very different type of magma. So you can think of that as, if you like, the 1883 event sort of cleared out the shallow magma chamber. So disrupted that chamber, we saw huge volumes evacuated, the formation of the caldera, and then perhaps a clear pathway for deeper magma less silica-rich magma, which is typical of sort of deeper crustal magmas, rising to the surface and building this new volcano of Anak Krakatau, the child of Krakatoa. Now that erupted more or less continuously, with sort of pauses of a year or a few years at times, right through to 2018, when during the evening of December the 22nd, about half that island failed in a large volcanic landslide. And that was during ongoing eruptive activity, but actually an eruption that had been going on right through 2018, since the summer. And without any recognised warning, the island collapsed. And this generated another tsunami, which once again had impacts on the coastlines of Java and Sumatra and killed over 400 people on those shorelines. So we can think about why Anak Krakatau failed in this way. Why was it unstable? And actually you can link that right back to the 1883 eruption. Because if we now look at a submarine map of Krakatau, and this is, although this is quite old, it's probably the sort of best map there is still of the caldera floor, we get a different view. So sea level's about sort of coming through here. So this is the island of Krakatau, this very steep one. And what we can see here is this area of very deep seawater, which is the caldera, the subsidence structure that formed in 1883. And one of the faults that controls the movement of this caldera is this one here. That's north, so this is the north-northwest alignment. And that fault essentially was moving along the volcanic feeder structure, the dike that was feeding the 1883 eruption. So that was a line of weakness, and it's the line in which the caldera subsided. That is still the alignment that is feeding Anak Krakatau today. So it's the same route through the crust that magma is taking to the surface. Now what that means is that's built up this volcano essentially on the edge of a fault scar. So it's built up this volcano on an asymmetrical underwater topographic structure. So Anak Krakatau has been accumulating and building up on this asymmetrical slope, which is inherently unstable. So if we took a cross-section through Anak Krakatau, it would look something like this. And this is based on sort of our reconstructions from maps through time. So if we take a slice through that scar, we can kind of see the edge of that caldera scarp here, how the volcano is built up asymmetrically with material accumulating on the gentle, shallow side, sort of failing off into the deeper caldera on the steep side, and so developing this inherent asymmetry. Now, the first stages of the eruption involved seawater interaction, so the magma mixed with seawater and produced ash-rich deposits. And once the vent was sufficiently high to get above sea level, the magma stopped interacting with seawater. Activity was therefore less explosive, and it built up lava flows and a cone of pyroclastic deposits. But those lava flows and that cone were sort of trapped on the asymmetrical structure that had come before it. So they were building up essentially on this inherently unstable position. So I'll just sort of talk through that with a series of maps. I'll go through these slides quite quickly, but we can sort of observe this asymmetry right from the start of Anak Krakatau's history. So if we go back to 1935, the very first map of the island, we can see already it's an asymmetrical structure. This is the northeast side, the material's accumulating happily on this gentle sort of platform, and on the southwest side, the material is falling away into the steep caldera rim. So this sets the scene for the next 80, 90 years or so until it failed. So if we go through the maps through time, we can see that that's even more exaggerated at this point in time. It's getting bigger, material starts to accumulate again, then erodes a little bit again. And this continued right through to 1960, which is the point at which the vent becomes closed off to seawater. The magma can no longer interact with seawater, and this changes the style of volcanic activity. So when magma doesn't interact with seawater, the eruptions can be much more gentle, and they start to produce lava flows. But those lava flows are sort of trapped by topography. They can only accumulate on this steep, unstable side of the volcano. And that continued right through to 2018. So we can see here it's a volcano of two halves, if you like. The lava flows on this half, and that earlier sort of ash-rich cone on the other half. And this was it just before it failed, essentially. So we can sort of almost map out how it accumulated on the northeast side versus the southwest side and the rate of that growth. And you can see that sort of that growth rate changed in 1960 to mainly accumulate on the unstable side, and you were just loading this slope through time. And eventually that reached a catastrophic point of failure, and we saw the collapse and the tsunami generation. Now, one thing that's sort of important to note is the timing of this was not predictable. It wasn't clearly linked to a particular shift in eruptive activity. So actually, the 2018 eruptions at Krakatau were quite intense, but they peaked in intensity in July and then in the summer, and really were declining into December, which was when the island collapsed on the 22nd of December. So there's first off not an easy route to have identified this was about to fail catastrophically. There was no sort of real reason to expect that. And the activity itself was not particularly unusual in style. This is something we've actually looked at in quite some detail, looking at the deposits produced before and after the collapse, as best as we can reconstruct them. So I'll just show very briefly some sort of results from that to give you some idea of what we can look at. But this is essentially the stratigraphy produced by the volcano immediately after the collapse. It's deposited directly actually on a tsunami deposit from the event itself. And we can look at things like the crystal content of the ash to understand the ascent rate of that magma, the chemical composition of that magma, how that behavior of the volcano may have shifted. Perhaps was there any implication of a change in eruptive activity that led to this failure? And we don't really find any evidence of that. It appears that the volcano essentially collapsed sort of passively, if you like, and that then affected the magmatic system because you sort of unloaded it very rapidly. But there's not really any shift in the magmatic system that can be implicated in causing the failure. This seems to really be a gravitational failure just linked to the loading of the volcano in this unstable setting. Now that's not good news for sort of forecasting potential because it means there wasn't necessarily a clear monitoring signal that one could have detected that preceded this event, except perhaps the long-term deformation of the volcano, which we can now recognize there were some signals that this flank was gradually moving with sort of incipient failure before the main event. I'll just skip over this. I think this is really just to sort of show how we can sort of reconstruct the changing behavior of the volcano through time from things like the shape and structures of the deposits that are produced to sort of identify shifts in eruptive behavior through time that are linked to the pre to post collapse magmatism. So as I say, we see some shifts in the rate at which magma is ascending. We think that's really a response to unloading, to decompression of the magma by the landslide, but not really the reverse. It's not really that the magmatic system is driving this change. Okay, so the model we sort of have arrived at for Krakatau is essentially this, that the volcano was of this sort of mature form in December. About half of it failed in this catastrophic landslide. It actually very, very rapidly rebuilt. It is now well on its way to looking, sort of to moving towards how it was in a pre-collapse setting. And over the coming decades, it will likely rebuild to a similar form. So already it is now producing lavas again and is in essentially a subaerial stage of activity. So very rapidly it regrew. And this was a sort of surprising observation, which we link essentially to the volcano being placed out of equilibrium by this catastrophic failure. So it sort of depressurized the magma system by removing about 400 meters of rock from above the storage zone. which allowed that uncompressed magma to then very rapidly ascend and reconstruct the volcano in a very, very short time period. So that's a very sort of interesting volcanic observation in terms of the links between surface load and subsurface stored magma, but it's really a consequence of the collapse rather than something we can understand to forecast the collapse itself. Now, for the sake of time, I'm going to whiz through this quite quickly, I think, but essentially we have been able to also reconstruct this event by looking at the seabed. The deposits from this massive landslide can be seen in the caldera. So the caldera today is now sort of half filled by this deposit from the failure of Anak Krakatau. That's what generated the tsunami. We can demonstrate that very clearly by finding the volume of this landslide and then by modeling that landslide volume as a tsunami source. So this is work done by colleagues at Southampton and at the University of Rhode Island. But they have essentially reconstructed that landslide and then used it as a tsunami source to test if that can replicate what was observed. And this does this very effectively. So we can see that the tsunami in 2018 can be explained completely by a landslide source. There's no need for an explosion source or a pyroclastic density current source. This is simply a landslide-generated tsunami capable of generating actually very extreme waves in these nearby islands. So a wave height here of 80 meters in terms of run-up on this island. So that's quite hard to imagine a wave running up against this cliff to a height of 80 meters. But that can be explained by a landslide of this size, a bit over a tenth of a cubic kilometer. And then if we sort of use that modeled source, is this going to play? Then we can see how that tsunami wave propagated out through the Sunda Straits, and again we can test that against observations from tide gauges and the known impact of this wave. And again, that landslide source, a single landslide event, is fully consistent actually with what's observed in terms of the impacts. So we can sort of demonstrate that this was, in some regards, quite a simple tsunami in terms of its mechanism. But as I say, that also makes this sort of challenging to forecast in that this really appears to be a gravity-driven event that's a consequence of just building up this volcano very rapidly. So the insights we get from this 2018 event was really that this volcano is sort of inherently asymmetrical and set up to fail in this way. And that is in turn reflecting the 1883 eruption and probably even going back even further in time, the tectonic setting of the Sunda Strait, which is controlling the feeder structures of this volcano. That means that this is perhaps something that's destined to play out again in terms of future instability, and means that I would argue that the lessons from this are quite important in terms of future monitoring strategies and signals of deformation. Particularly if we want to understand the timescale of that and the future growth of the volcano and when it may become unstable in the future. And the tsunami model is consistent with a simple, single sort of landslide source that can explain the impacts of the event. Now, volcanic landslides are a relatively sort of widespread common process on the timescale of volcanoes. On this scale, they're not sort of well known simply because few have happened historically. But I've already mentioned the Mount St. Helens eruption, and as I say, this event at Ritter Island would be a counterpart. Now, we only have sort of one clear drawing of Ritter before it failed, and that's this one here. But based on descriptions at the time, it appears this is reasonably accurate, and this was really quite a prominent volcano, not unlike the appearance of Krakatau, actually. And all that was left after this catastrophic event in 1888 is this crescent-shaped remnant that was left behind. So again, this was an extremely large volcanic landslide, probably in historical times the largest volcanic landslide globally, so about twice the size of the Mount St. Helens failure. But all of this really is left underwater. So this is now a view of the seafloor, and we can see the volcanic cone is a much larger structure than you'd know from the island up here. And we can now really see the mouth of this landslide scar, this sort of amphitheatre that's opening to the west in this case, and we can see the new volcano that's building up entirely beneath sea level. And all this topography here, a bit like at Krakatau, with the deposit from that landslide. And that deposit actually runs out for around 80 kilometres, about 50 miles beneath the seafloor. So that can be mapped out over a huge area of seafloor. This is now a seafloor map. That crescent-shaped island is down here, tiny on the scale of this map. These are the sort of coarse landslide deposits, and then the fine-grained landslide deposit can be traced over a huge area. And this is data that we've collected with German colleagues, sort of mapping the seabed with geophysical data to understand the volume of this event, how it's moved, how it's interacted with the seafloor, and again to really understand this as a tsunami source. And the tsunami from this event, although I said earlier it's not well documented, there are descriptions that describe this to distances of over 500 kilometres from the volcano. So this did really have major regional impacts and likely devastated coastlines around the volcano. I'll whiz through this, I think. It's a little bit complex to explain, except that this event, again, appears to have shifted behaviour at the volcano. So as a consequence of the landslide, there seems to have been a change in magmatic activity at the volcano, which we can detect from the geochemistry of the products that were erupted. So it's another example where these massive failures appear to disrupt the subsurface magma system and to change eruptive behaviour, maybe the rate of eruption, as we saw at Krakatau. In this case, actually the chemistry of the magmas that are reaching the surface as well. So again, we have a volcano that we think was inherently unstable at Ritter Island. We found some evidence that it was deforming actually over a long time scale, not just catastrophically in 1888. So it has some analogies to Anak Krakatau, and perhaps there are other volcanoes like this as well that are deforming in this way. But this event was around 10 times larger than the 2018 failure of Anak Krakatau, so it's a much bigger event and had a much further reach as a consequence of that. Okay, so I'm just going to finish on the Hunga Tonga event, the most recent of these events, which was rather different again and sort of brings some new complexity to understanding volcanic tsunamis. And as far as we understand, this can really be categorized as an explosive eruption-driven tsunami from a shallowly submerged explosive event. That interaction with seawater can, I think, be connected to the extreme height of this eruption column, which reached 50 kilometers or more into the atmosphere. So this is a satellite view of the umbrella cloud from this event. And as I said earlier, the atmospheric pressure waves from this event were detectable right around the world. So very intense energy release. Now this is, I think, a volcano that helps us sort of think cautiously, I suppose, about what we understand about the risk of these types of events. Because I don't think any volcanologist would really have looked at this volcano before 2022 and thought this is primed for a massive eruption, a sort of globally significant eruption that will cause sort of extreme devastation. I really don't think that was recognised, and I would say even based on our current understanding of sort of volcanic systems would not even be what one would forecast based on the type of magmas erupting and the styles of eruptions, which were relatively sort of gentle in terms of scale and explosivity, and were erupting sort of relatively silica-poor magmas, so basalts, basaltic andesites, building these small cones. So it wasn't a volcano that sort of we expected to be primed for this massive type of caldera-forming eruption. It wasn't monitored. It's in a very isolated area. It wasn't a volcano that sort of warranted huge amounts of attention. And yet, in 2022, January, the eruption behaviour suddenly intensified dramatically. I guess in that regard, it does have something in common with Krakatau, even though the magma type is rather different. And this sort of intensification was recognised as something really quite unusual in its behaviour, to the extent that the Tongan Geological Services had issued tsunami warnings, potentially linked to explosive eruptions. And that probably saved a lot of lives on the main island of Tonga. So even before the main event, this intensive activity had destroyed this cone that had been there before, and then the main event left really very little of either of these islands. So there was evidence for large caldera subsidence and a very destructive event at the volcano itself. So not something that we would have expected to happen at this volcano, which perhaps questions our understanding of many volcanoes, particularly in this sort of less well-studied part of the Pacific, where there are a large number of volcanic islands. This generated a tsunami with heights of around 20 meters at a distance of 65 kilometers. So that's larger than the 2018 Krakatau tsunami. Substantial deepening of the caldera structure at Hunga Tonga, evidence for extensive submarine pyroclastic currents, and a complex tsunami source linked to that shallow explosion. I'm not showing it here actually, but again, we have worked on modelling of this event, and it seems that explosive source can explain the characteristics of the tsunami, potentially coupled with these pyroclastic currents. So just if we sort of contrast those two events and how this leads to some challenges for mitigating and managing these types of hazards. At Hunga Tonga, there was some sort of warning. I mentioned Tongan Geological Services responding to this, essentially based, although it was unmonitored, there was simply an observed change of eruptive style. So this was recognised as something out of the ordinary. And with monitoring, perhaps that would have been sort of more identifiable even with sort of more time ahead of the event. Now the travel time was about 15 minutes between that tsunami being generated and reaching populated shorelines, but because of that recognition and awareness, and even the fact this occurred in the daytime, so people could see the change in behaviour, that likely saved a lot of lives through self-evacuation to higher ground. Now that did not occur at Anak Krakatau because this occurred at night or in the early evening, in the dark. There was no recognition of a shift in eruptive style, probably wasn't even a shift in eruptive style, so this was sort of the first people knew about this event was actually when the tsunami hit the shoreline on Java. So it wasn't observed until this tsunami arrived. And it wasn't even initially recognised that this was a volcanic tsunami or what this event was. But again, a very short time. And the key point here actually is this very short warning time. So unless we can get to a position where you can recognise the precursors to these events, the prospect of issuing effective warnings is very low, because this is an extremely short time between recognising event, issuing alarms or warning systems, people knowing what to do to evacuate and so on. So this makes these events very challenging because of that short warning time. Okay, so I'm going to finish with, some slightly text-heavy slides, but just a few key points, I suppose, that I wanted to make from this talk. So first of all, volcanic tsunamis can be produced by diverse mechanisms. There's no sort of single type of volcanic tsunami generating process. That makes them difficult to sort of forecast because every volcano has its own sort of distinct setting that might lead to different behaviors. Identifying the behavior that leads to these unusual, atypical events is challenging, particularly recognizing the timing of those events. Even if we can do that, the warning timescales would be very short, and therefore preparation and warning networks would need to be highly efficient to sort of manage the impact of these events. And this sort of makes these difficult to build into hazard management plans, I suppose, in general, because they're infrequent, unusual and predictable types of events that depart from the normal, typical activity of any individual volcano. So how could we sort of move on from that? I think volcano deformation and flank instability is a really sort of important part of understanding the drivers of some of these processes at least. Many volcanoes are potentially prone to collapse in a way that's not likely to be detected by our standard sort of magmatic monitoring techniques. Warning systems need to be developed that are highly efficient and can deal with this type of event. And I think there's a sort of question as to how to really communicate and raise awareness of this type of process without being sort of unduly alarmist, given that these are low frequency, rare events, but we have to recognize they do have the potential for extreme impacts. So sort of raising awareness and maintaining awareness, but in a balanced, effective way, is difficult for hazards of this type. Okay, I will stop there. Hope I haven't run too much over time, and happy to answer any questions on that as well.
It falls to me to do the most thanks, and firstly, could I say a huge thank you for giving us a much deeper understanding of processes that create these waves. I think we probably all just thought it was an eruption, and that's that. This is a real insight into a much deeper understanding of the volcanic process. So thank you very much for that. And I think as well, giving us a tour of a landscape that most of us have only heard of in the myth of the 1880s. So I'll ask the membership to join me in the usual way in thanking Sebastian for a wonderful evening.